Morning. Welcome to the PACE webinar on COVID-19 indoor air, ventilation and energy efficiency for building owners. We're just waiting for folks to come in. We'll get started in a minute. Well, it's a little bit past the hour and we've got about 150 people on the call so far. We're expecting about twice that, and I see the attendance is still steadily ticking up here. But we'll get started with some of the logistics because we have a lot of great information to cover. Hello everybody, I'm Zach Swank. I'm with Partners for a Clean Environment. Partners for a Clean Environment is Boulder County's one-stop shop for business sustainability. And we provide free expert advising, rebates and incentives for energy efficiency, waste reduction, water efficiency, and transportation. And we're the host of today's webinar. The webinar is going to be broken up into two presentation parts. The first being the science of COVID-19 in indoor air, and then the second, what to do about it. Then we should have 20 minutes for your Q&A at the end. When we get to that section or throughout the webinar, please use the Q&A feature to ask questions rather than the chat. It really helps us organize it. And we have quite a few people on the call today, so that's particularly helpful. And then finally, the webinar recording will be posted and shared. I know that's always a question, so we'll share that out with all of the registered attendees. Of course, a few disclaimers on anything on COVID. The scientific understanding of COVID is still evolving, and the recommendations made today will likely continue to change as we understand the disease more over time. Second, the opinions expressed today represent the speakers, not their organizations. And third, we're providing our best recommendations to minimize risk, but risk of COVID-19 cannot be eliminated entirely. And then finally, if you are making or thinking about making any changes to your heating, ventilation, and air conditioning system, contact a professional before making those changes. So getting into what you came for, I am pleased to welcome Dr. Kristen Fedak, who is the environmental epidemiologist and researcher at Colorado State University, as well as the occupational health coordinator with the Colorado Department of Public Health and Environment, known as CDPHE. In CDPHE's COVID-19 response, Kristen serves as the subject matter expert for industry workplace prevention, mitigation, and response. And our second speaker today is Jim Zarske. Jim is the Director of Sustainability Services at NORESCO, one of the largest energy services and sustainability consulting firms. He's a licensed PE, CEM, lead AP with more than 20 years of engineering experience with a focus on building energy efficiency, including energy auditing, retrocommissioning, and HVAC design. So thrilled to have such great speakers today on this topic, and we've got a really great presentation for you, packed full of information. So without further ado, I will turn it over to Kristen to take it away from here.
Thank you, Zach, and thanks for the introduction. I'm going to speak today about COVID-19 and indoor air, focusing on what we know, but also sort of what we don't know right now about bioaerosols and COVID-19 transmission. And quickly, Zach, I think I lost control of your screen there. So could you share it again with me so I can?
Yes. Oh, hold on 1 second here. Let me go back here. All right.
That looks better now. Great.
Have it.
Okay, so jumping right into it. Everybody's main question right now, is SARS-CoV-2 airborne? And importantly, when I say airborne here, I'm talking about it in the way that the general public is talking about it right now, which really means I'm asking, can SARS-CoV-2 spread through these sort of small particles that float around in the air and spread longer distances from the source, sort of linger after the person has left the space? And to jump right to the chase, the answer I have for you is I don't really know, or to put it more accurately, the scientific community right now doesn't know. But I can share a little more information for you than just that. So today, in the next 10 minutes or so, I plan to cover a few sort of crucial questions, give you some information about what we mean by airborne and this kind of aerosol and droplet transmission, what we currently know about routes of transmission for SARS-CoV-2, and why it is we don't know whether that airborne or aerosol transmission is occurring, but think it might be. And then finally, what the implications are for public health and infection control if SARS-CoV-2 is airborne in this sense. So what do we mean by airborne, aerosol, and droplet? Aerosols is a term that refers to any solid or liquid particle suspended in gas or suspended in the air. So airborne really just means that a particle is in the air and hasn't yet settled out. This distinction we hear about right now in the media about whether SARS-CoV-2 is airborne is a little bit of a misnomer because the question really comes down to particle size. So aerosols in our world come in a variety of different sizes depending on the source. For reference, we can think of larger particles like visible dust or sort of microscopic pollen. We have sort of middle-sized particles that might come from things like abrasive dust, so sort of industrial type of activities that create these sort of middle-sized particles. Where you might start considering PPE to protect the employee or the worker from exposure to those smaller particles. We have smoke, which is quite popular right now in the state of Colorado and California as well. So smoke from wildfires as well as smoke from energy production or air pollution, where you're talking about small enough particles that you can't see them, but when you get a high enough concentration of them, you get these sort of visible plumes of smoke. And then on the very far side comes things like nanoparticles, so particles that fall in this really small nanometer as opposed to micrometer size. So we've got kind of this spectrum of what we might refer to as aerosols, and understanding the different sizes is really important for thinking about how they behave in our physical world. Respiratory aerosols is a term that we think about with infectious disease. So essentially diseases that are spread through this respiratory route. We want to think about, you know, what are those aerosols that the diseases are spread on. So you can essentially think of a respiratory aerosol as that sort of particle of liquids and solids, so be it spit and kind of fluid, that carries proteins and other molecules. Of interest for us here is carrying viruses. And these respiratory aerosols, rather than coming from a source like a generation of smoke from a power plant, they're coming from a source that is a person. When they do something like talk, sneeze, cough, things like that. So we can define our respiratory aerosols across a variety of sizes as well, just like we do other types of aerosols. When we sneeze and cough, we tend to produce some larger aerosols, as well as some of the smaller ones, where activities like simply breathing are going to produce mainly smaller aerosols and not reach that larger size. Of course, things like talking fall somewhere in the middle, and these are not mutually exclusive types of categories, right? So I'm talking right now, so I would say I'm kind of in that middle range of particle sizes. But of course, in order to talk, I'm also breathing and probably emitting a lot of smaller particles as well. So where does SARS-CoV-2 fit in? The virus itself on its sort of standalone form is about 120 micrometers in, or nanometers in size, 0.12 microns. But of course, SARS-CoV-2 is not sort of traveling on its own. It is kind of agglomerated onto these respiratory particles. So the main question we have then is what size particles are capable of carrying this virus? How far do those particles carry it and under what conditions so that someone else is exposed? And also, what size particles are able to carry enough viable virus that the recipient, that person who is exposed to that particle, actually becomes sick as a result of that exposure? So like I said, the viruses don't really travel in this free form. They're latched on to this respiratory fluid in these different particles. So due to particle physics, the size of that particle dictates how it acts, how long it stays aloft in the air, how far it travels from the source that expels it, from that person who's doing that talking, breathing, coughing, and how quickly it falls down to settle on surfaces. The size of the particle also impacts when it is inhaled, how deeply it deposits into your respiratory system, which might play a role in your likelihood of infection taking hold, as well as how efficiently it is then removed by things like masks or filters. Essentially, to simplify all of aerosol science field into one statement, the smaller the particle, the further it can travel before it settles out, almost the more gas-like it acts, and the larger the particle it is, the faster it sort of drops out, the closer to that source it stays. So focusing on that kind of question of which size particles do we care about for SARS-CoV-2? We can essentially dichotomize this, and we see the media using these phrases a lot, as either respiratory droplets, which are larger size particles, or respiratory aerosols, which are the smaller particles. Those larger respiratory droplets have a short residence time in the air and effectively settle out quickly. So they sort of think of them as dropping to the ground or landing onto surfaces that are within a close range of the source, the person who's sick and emitting. And they do that pretty quickly. Therefore, if larger droplets are carrying SARS-CoV-2, in order to transmit that virus to another person, that person has to be within a pretty close range of the sick individual. And while within that close range, the person has to act in a way that produces some of those large droplets. Respiratory droplets respiratory aerosols on the smaller side are emitted when sort of doing normal things like talking and breathing. And so because they're smaller, they don't settle out of the air as quickly. They sort of disperse and can move further distances from the source. So if smaller respiratory aerosols are carrying SARS-CoV-2, to transmit that virus to another person, that other person can be further away. They maybe don't have to have that direct contact with the other person. So maybe they occupy that space, that airspace, a couple of minutes after the sick person has left. And that sick individual doesn't necessarily have to be acting sick, right? They can be breathing or talking normally, producing those small aerosols. They don't have to be doing something we think of as a sick person doing, like sneezing or coughing. So what do we know currently about the routes of transmission for SARS-CoV-2 to answer these kind of questions about how it's transmitted? We know from the current cases and the epidemiological studies on those cases that droplet transmission happens. People who have direct, sort of unmitigated close contact with known cases get sick. People whose contact was less close don't get sick to quite the same extent. We have studies that have shown that what we call the secondary attack rate, so that sort of person number one is your case, how many people around them get sick. We see that attack rate is greatest among household contacts, so people who live in the same house and therefore spend a lot of time in close proximity to the sick individual. That risk of spreading to a secondary contact is a lot lower for other types of interpersonal contacts that we've been able to study. For example, there's data that shows that sharing a meal with an individual who is sick has about a 7% attack rate, and a passing interaction like shopping or kind of those retail exchanges is less than 1%. So this really helps suggest that those close contact droplet transmission is occurring and is sort of responsible for a lot of these cases. We also see that in hospitals and healthcare settings, the personal protective equipment that is put in place largely to inhibit that droplet transmission works to mitigate those close contacts that occur between, the sick individual and the healthcare provider. Additionally, we are seeing outbreaks occurring most commonly in crowded situations. So these are things like industrial workplaces where people work in very close proximity to each other, correctional facilities and homeless shelters where the living conditions are quite crowded, and bars where people hang out close together and maybe talk a little too loud because they're inhibited by other things. And so these crowded situations, we're seeing a lot of outbreaks occurring. Which suggests again that droplet close range transmission is responsible. We comparatively are not seeing outbreaks occur as often outdoors, which is interesting, particularly when you think about certain outdoor but also still somewhat crowded situations, which does suggest that some of this sort of ventilation or dilution of the air is beneficial. But that droplet transmission doesn't explain everything that's happening. And this is where the concern over aerosol transmission comes into play. Not all of our cases have known close contact with other cases, right? So there's something else that's going on that's responsible for some level of SARS-CoV-2 transmission. Now, it's challenging to say that that means that it must be aerosols, because with identifying that sort of point source of who was the exposure for all cases, we're challenged by the fact that with SARS-CoV-2, we see peak infectiousness occurring a few days before symptoms start and at that initial onset of symptoms. So it's possible that some of these cases who don't know where they got it from, who don't identify a kind of close contact with another case, simply didn't know that they had it because that close contact with another individual they didn't realize that other individual was sick. We also see that around 15 to maybe as high as 45% of cases remain asymptomatic during their entire illness. So again, people may be having these close contact interactions as their source of their infection, but we don't know because of this kind of asymptomatic and pre-symptomatic spread. We do see that face coverings slow the rate of transmission and have slowed our epidemic. Particularly, as I already mentioned, PPE has worked really well as a type of source control for known cases and for healthcare workers who are in that close contact. And we see that this sort of mask for everybody recommendation that came in the last couple of months has really helped with that asymptomatic and pre-symptomatic close contact situation to reduce that spread. This masking, sort of mask for all, though, may also be doing something to help with smaller aerosols. N95 masks are, as hopefully many on this call know, are great because they effectively filter out 95% or greater of particles within that full size range of concern. So with N95s, we don't have to worry about the question of is it large particles or small, because that mask is really helping with everything. As you start working your way into lesser quality masks, particularly working down to this idea of homemade masks or simple cloth face coverings, those effectiveness is going to vary. Studies that have looked at how well universal masking have worked have shown that it definitely reduces and slows that rate of transmission. And we know that masks, even the least efficient masks, those sort of cloth face coverings of the most simple style, are helping to stop large droplet transmission. However, we don't see that universal masking, particularly of these homemade masks, is completely eliminating transmission, which does kind of push towards that idea that maybe there's some aerosol spread occurring. And then finally, we have some of these sort of case studies that really point towards transmission events where we think small aerosols were responsible. The Skagit County Choir in Washington is a big one that happened very early on in the pandemic. There's also the restaurant in China where the AC was thought to be responsible, as well as a more recent study that looked at potentially spread occurring through the use of a shared elevator in an apartment building. However, if the small aerosol transmission was really a large driving factor of this pandemic, I think we would have more than just a few of these sort of case studies to point at this. So why don't we know if aerosol transmission is occurring, but think it could be? And now my slides aren't moving forward, even though I'm trying to get them to here. Okay, so back to that question. Is SARS-CoV-2 airborne? My answer for you is maybe. So to summarize it up, we have this information that shows that SARS-CoV-2 is currently spreading more efficiently than influenza does, but not as efficiently as measles. Influenza is very well established to be that droplet close contact transmission. Measles is very well known to be a small aerosol and a very small amount of viral load needed to cause that. So this is suggesting that SARS-CoV-2 is kind of falling in the middle with maybe both things occurring. That aerosol risk is probably there, but it's a really secondary risk compared to that droplet transmission. We also don't know if what we're seeing with that aerosol risk really relates to then also the ability to transmit viable virus, but maybe a higher dose is needed. So you may have SARS-CoV-2 traveling on small viruses, but if the concentrations of that aerosol are kept diluted, that lowers the risk. Or maybe the small aerosols are carrying virus, but not enough of that virus to really be effective as a way for transmission for most people. Our epidemiology is showing that it definitely is spreading through person-to-person contact, through respiratory droplets in these kind of close contact settings. And that's known, but we see that staying distant and wearing masks, which works to stop those large droplets, disrupts transmission, but not 100%. So aerosols could be the responsible piece for this. That's relating to that last bit of transmission we can't seem to stop with these other controls. Or it could be that maybe there's some behavioral factors playing in, people not wearing masks as well as they should, or staying distanced as well as we really need to. And trying to switch to the next slide here. Thanks, Zach. So some of our critical questions that remain are, what size particles are generated by people from the different activities that they do, kind of getting a better understanding of what are those size distributions from talking versus breathing versus singing or other activities. And then looking at those different size distributions, we really don't know right now what sizes of particles can carry the SARS-CoV-2 virus and how long they're viable on those particles. And then we have a lot to learn still about the infectious dose and disease relationship, essentially how much viral exposure is needed to establish infection. And that's a critical piece of understanding whether these smaller particles, which inherently are going to carry less virus than a larger particle, is really capable of transmitting the disease. And then finally, this question of whether some of these more behavioral and environmental factors are impacting that exposure risk, which sort of conflates our ability to really define this difference between, is it the droplet spread occurring, or is it that smaller aerosol spread in some of these situations? So finally, what are the implications of this for public health and infection control? Essentially, what should you do with the information I just told you? My main point is that we should continue to do what we know is helping slow transmission and reduce risk. So wearing masks and face coverings, staying distant, physically distant from other people, and certainly if you are sick or think you may be sick or were exposed to someone who is sick, stay home and don't interact with other people. Essentially stop that chain of any type of spread. But we know that these things are not a 100% guarantee. Maybe it's a bit of just bad luck that we're not perfect at wearing masks or the perfect types of masks, that staying distant is really hard to figure out while going about our everyday lives. Or maybe it's that there's some of this small aerosol spread that is occurring. So if it is that small aerosol spread occurring, you're already doing the other things to reduce your risk in ways we know, but want to go that extra step. Changes to ventilation could be a useful additional measure. However, attempting to change that ventilation, if we really don't know what we're doing, what we're trying to change or why, could inadvertently make things worse. So I really caution to, if you're unsure, don't do anything drastic. Particularly, I would think about costly changes where we don't really know if they're worth it at this point, because we don't fully understand that risk from small aerosol transmission. It's hard to say what amount of benefit is then gained by some of these changes that address small aerosol transmission. But with that in mind, thank you for your time and listening. And I'm gonna pass it over to Jim to talk about some more ideas of that, what you can do.
Great, thank you, Kristen. That was a great introduction on the aerosol and COVID and so forth. So now I'm going to talk about that ventilation piece, the part that Kristen left off with, and talk about your mechanical systems, namely your HVAC systems, and what you can do to maximize the performance out of those systems, these days. Let me see if I can get this to advance. Okay, so the current topics I'm going to be talking about, I'm going to give you a little bit of background on kind of building filtration 101, ventilation 101. I'll talk about the do's and don'ts of HVAC modifications, keeping energy efficiency in mind, and then how to get help. So let's see. So in order to know what type of filter to use, one needs to know what you're trying to filter, right? Most systems are designed around filtering particulate matter and protecting the HVAC equipment, the coils, the motors, et cetera. In labs and hospitals and industrial environments where there are known contaminants, the HVAC systems are designed to control and minimize those contaminants from being inhaled by the occupants. As Kristen discussed, small particles are measured in microns or a micrometer, which translates to how the filters are rated. So as you can see here, borrowing from Kristen's slides, you can kind of see where different size particles fall within the micron range, or that symbol there is for a micrometer. And just for reference, 1,000 microns or micrometers equals 1 millimeter. So very small. Let's see here. Apologize for the delay on the advancement. So that's where COVID falls. And then as you can see here, filters are rated based on the size particles they can filter. Most of you have heard of MERV, or Minimum Efficiency Reporting Value for filters. MERV is an acronym. And I've included the most common ones and the particle sizes they can filter. MERV filters do range from 1 to 20 in efficiency. The higher the MERV rating, the more it can filter, and the percent of particles in that range that can be tracked. There's also Hepa filters, which I'm sure, again, a lot of you have heard of. Hepa is another acronym which stands for High Efficiency Particulate Air Filter. While HEPA filters can filter many indoor air particles, they won't be successful with the smallest viruses. However, like Kristen just talked about, these viruses often cling to water droplets and other larger particles in the air that can be filtered through a HEPA filter. Also, their filter media is very fine, which means it takes more fan energy to push the same amount of air through them, which the supply fans likely in our buildings that don't have HEPA filters were not designed or sized to do. Think about how much more energy it takes to breathe through a mask that we're wearing these days. And that's the same amount of energy that a fan motor has to overcome with high efficiency filters. So then I'm going to talk a little bit about building ventilation. So you can understand improvements you can possibly make to your ventilation system. ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. Through research, they regularly publish many standards and guidelines that engineers use when designing HVAC systems in buildings and are referenced in many local building codes and standards and often required. ASHRAE these days, just so you know, is publishing a lot around COVID. They're a great resource if you're looking for the latest and greatest recommendations. But to understand how buildings are ventilated and what adjustments can be made to the amount of outside air, I'm going to briefly cover how these systems are designed. ASHRAE Standard 62.1 is their ventilation standard for acceptable indoor air quality, or IAQ, which was first published in 1973 and is updated every 3 years. This standard provides the minimum ventilation rates per space type and per person and the filtration requirements. When a mechanical engineer is sizing the HVAC equipment, they factor in the amount of outside air that needs conditioning on design, heating, and cooling days, based on the designed or maximum occupancy for that building. Well, the reality is that most buildings rarely reach design occupancy they were designed for. So then you might be wondering, how do you ventilate a building properly? Meaning, how do you not over or under ventilate it? Well, a common technology in larger buildings is demand controlled ventilation, or DCV, which commonly uses carbon dioxide sensors to increase or decrease the amount of ventilation based on occupancy loading. As you know, CO2 comes from humans, and it is cheap to measure and an overall good proxy of how well a space is ventilated. This works great in spaces that can see big swings in occupancy, like conference rooms, classrooms, large open working spaces, retail spaces, and auditoriums, to name a few. Buildings that don't have DCV can be overventilated, and even over time, buildings can be underventilated if adjustments to the minimum outside air are made by facilities or maintenance staff without considering the actual occupancy of the building. So how does one determine that the existing or even new building is properly ventilated? You might be wondering. Well, that's where a tab or testing, adjusting, and balancing contractors come into place. They will actually measure the amount of outside air and adjust the minimum setting on the outside air dampers to match either the designed minimum outside air on the drawings for new buildings or required guidance on the existing building's actual occupancy and make adjustments accordingly. And again, this guidance is usually provided through a mechanical engineer, which is handed off to the tab contractor. So you might be wondering, can you just increase the building to 100% outside air 100% of the time? The answer is no. If the system isn't designed to do that, because if it was mild outside, it would be okay, right, to bring in a lot of outside air. In fact, that's the way economizer cycles work. They bring in 100% outside air instead of using the mechanical cooling. But when it's really hot or really cold outside, the system would struggle to keep up and lead to comfort problems. Plus, it would also come at a large energy expense too, and not meet energy code. So systems that are designed for 100% outside air, which again includes labs and hospitals, for example, have either heat recovery and or large heating and cooling coils to adequately condition large amounts of outside air. Another question floating around is, if the building HVAC systems are off, does the space need to be flushed after sitting stagnant? Sure, but not for long when the system is turned back on. Ventilation is measured in airflow, or cubic feet per minute, but also what we call ACH, or air changes per hour, which is the amount of volume of air replaced with fresh air per hour. For example, a 10,000 square foot space designed for 20% outside air would would provide approximately 1.2 air changes per hour. Plus, the reality is that most buildings are not sitting stagnant per most lease agreements. Most people assume that buildings are sitting stagnant because no one is in them, but unfortunately, that's not the case. So now I'm going to get into kind of the do's and don'ts here of HVAC modifications. The first one is, does retro commissioning just mean call your contractor out for their quarterly maintenance? No, it doesn't. Retro commissioning means hiring an engineering firm that specializes in this service to determine if the building is operating as designed. This includes checking calibration of control points within the HVAC equipment, tab as we talked about, reviewing control sequences for comfort and energy efficiency, and summarizing the findings and recommendations in the report. I mean, that's frankly the first thing you should do. Is your building operating as it should? Some HVAC systems don't provide any outside air. Granted, this is usually in small facilities and retail suites. So that's the first check. Do you have ventilation or not? And then that will be covered in the RCX if you have that done. Then determine how to maximize the design capabilities of your HVAC system in terms of outside air ventilation and filtration. Now, if you have a larger facility and you want data to review before investing in any equipment, then consider getting an indoor air quality assessment, which includes measuring carbon dioxide over time, which again is a good proxy of how well ventilated the space is under normal operations, and also particulate matter, or PM, the amount of particulates that viruses and bacteria cling to that are floating around in your space. You may have seen the terms PM 2.5 or PM 10. That refers to particulate matter, and then that's the size in microns, the 2.5 or the 10. And that will also be measured as part of an indoor air quality assessment. Is your HVAC, now, if your HVAC system is not capable of these ventilation and filtration enhancements, do you just throw your hands in the air and say, sorry, can't do anything, we're done? No, the answer is there are other things you can do. So what you can do is complement what your HVAC system is capable of by using portable HEPA filtration. As we talked about, HEPA filters are very efficient. And then something I haven't mentioned so far is UVC light. UVC has been demonstrated to kill the coronavirus and other bacteria and viruses, and they come in portable form as well. And you may have been in hospitals or waiting rooms that actually have the UV lights attached to the wall. Both of these are good economical portable options to complement what your HVAC system cannot fully provide you. Also, redirecting supplier flows so they don't become indirect. A lot of these case studies that Kristen mentioned show that blowing the air across the room, if it can pick up the aerosols and transmit them, are not good and can lead to transmission. So redirecting those airflows is a good practice. If your system hasn't been air balanced in a long time, then have the airflow checked and adjusted to ensure it meets the design and is adequate. And then if you want the comfort and assurance of your building's air quality over time, consider installing IAQ monitoring stations with public displays. These have become very economical over the years and will allow you and your occupancy the ability to check the air quality in different spaces through your phone, like you check the weather in different cities, believe it or not. That technology does exist today. The final do's for HVAC system modifications is, while you're checking to make sure your building brings in the maximum possible ventilation, it's also important to make sure the exhaust systems are working correctly so the building doesn't become overpressurized with this added ventilation that you're looking at increasing, meaning you don't want the front doors of your building blowing open. Consider installing better controls in your building that allow for adjusting the operation of the building based on actual occupancy, which includes DCV, as we talked about, and also setbacks. Operable windows are great if you have them in your building. However, they aren't great when it's 10 degrees or 90 degrees out. So this can help when the weather is mild. Great, open the front doors, open the windows. But the reality is that you're going to rely on your HVAC equipment and any supplemental systems you install long-term and through all seasons. Let your staff and building occupants know what you have done to make your space safer. Communicate any changes in policies or actions people need to do when they're in your building. There are certifications out there that support and demonstrate these recommendations, but you can still advertise these improvements in the absence of investing in a formal certification. Lastly, continue to maintain your building. Some of the don'ts I wanted to cover. Oops, I need to go back up. Oh, there we go. Okay. Well, of course, doing nothing, right? While you're checking to make sure your building, unless you're 100% sure that you're doing everything you can to make your building safe, I recommend not doing anything. Even a quick discussion and a building walkthrough with an engineer can open your eyes to whether you need to consider making some changes to improve your building's health. And also talk to someone that's a professional, not a salesperson. As I mentioned, most HVAC systems are not designed for 100% outside air 100% of the year. This goes for Hepa filters too. Because they filter out a lot of the fine particles, they also require a stronger fan to push that air through it. 100% outside air systems and HEPA filtrations are common in labs and medical facilities, as I mentioned, but most commercial office buildings don't have these systems in them. Portable fans are not recommended because there are case studies out there supporting the spread of the virus through air currents carrying it across the room. If you are unsure about purchasing a project, consult with a professional that is not an equipment representative and can give you an unbiased professional opinion. There are also some filtering systems out there that are referred to as an ionizer or use the ionization process. These can sometimes produce ozone, which is an air pollutant. Make sure you review the literature of these products or consult with a professional before buying one. So energy efficiency, how does that weave into all this? Well, like a car, a tuned up building is an efficient, comfortable building, just like your car. And of course, I can't sugarcoat the impact of your building using more energy with some of these suggestions. Adding filtration, increasing ventilation you have to condition, plugging in portable equipment will also increase the energy use. However, energy use can be minimized through good controls like demand control ventilation. For example, if your outside air is sized for 100 people in your building, but you only have 5 in it right now, DCV will help with that. Setbacks and temporary override controls are great. So program a core schedule for your building, like a Monday through Friday, 8 to 5. And then if people come in on the weekends or weeknights, have temporary override controls. They work great. You can also offset energy use by making the rest of the building more energy efficient. So some suggestions here is that if you are in a position to where you want to replace your equipment or it's getting old, there are technologies to improve the efficiency, including energy recovery ventilators, evaporative cooling, evaporative condensing, making sure you have air side and or water side economizers, depending on the side of your building, and then overall better controls. So what I wanted to close out with is how to get help. And I kind of broke this up into 2 categories. There's 2 sets of service groups out there. There's the engineering firms and the contractors. And both provide valuable services to our industry, but they are different. And it's important for you to understand the difference so you know where to seek help based off your needs. So I'll highlight a couple here, but I'll let you read most of them. An engineering firm, of course, will retro commission, do an energy audit on your facility. They're going to make recommendations based off the latest research guidelines and building codes. I mentioned they can do indoor air quality assessments. They can commission any new equipment you have installed. If your system needs to be designed or redesigned, they'll help you with that. They can check the sizing of equipment, provide certifications, and they will not use rule of thumbs. Whereas a contractor, they will implement the recommendations from the engineering firm. They maintain, fix, replace, and install your HVAC equipment. They perform tab. They'll adjust the settings within your equipment, and then they'll set up and program controls. And now I'm going to turn it back to Zach here to finish out the slideshow.
Thanks, Jim. And because of what PACE is and what we do, it would be remiss not to mention that there's another source where you can get help, and that's often your local government and utility, which are a source for rebates for energy efficiency if you are making upgrades and improvements to your system. PACE, for example, offers both on-site assessments and advice for free, as well as rebates to businesses in Boulder County. But if you're not in Boulder County, say if you're in Denver, Fort Collins, elsewhere around the state, There are peer programs to PACE around the state as well, and often there are incentives available from your utility, if not your city as well. So reach out to your city and utility representatives to check. And some common equipment that typically has rebates are new high efficiency rooftop units, the fresh air economizers that Jim talked about that bring in outside fresh air, direct evaporative pre-cooling, which improves the efficiency of your existing equipment, evaporative cooling to replace your air conditioning system or augment it, say if you've got a retail environment and you want to have the door open all day, and then of course programmable thermostats. So that concludes our portion of the presentation, and we have PACE representatives Elizabeth French and Denise Grimm, who have been monitoring the Q&A throughout the presentation, and will now pose some questions to the panelists. But just a friendly reminder, if you do have questions, use that Q&A feature, which should appear in that black bar at the bottom of your screen. Denise and Elizabeth?
Good morning, everyone. It looks like we have about 12 minutes. Can everybody hear me okay?
Yep.
Great. I've got about 11, 12 minutes to answer some questions here. Looks like the first one is related to outside air. So I guess a question for you, Jim. During the shoulder season, what is the best way to ensure you have sufficient outside air? Basically when systems aren't running much.
Yeah, that's a great question. So, yeah, during the shoulder seasons, the weather is mild, right? We're somewhere between the 50s and 70s out there. And depending on the type of HVAC system you have, if your system actually has an economizer, the whole point of that economizer is to minimize the use of mechanical cooling, which means it's actually going to open up to close to 100% outside air, and will be ventilating your space with quite a bit of outside air. Now, if your system does not, if your rooftop unit does not have an economizer, then the other alternative is that you have a fixed amount of outside air, and that was fixed based off the design of your building, and that you can't adjust. That's fixed. However, you can have that replaced with a full functional economizer, which will allow you to bring in outside air during the shoulder seasons. And then the third option is if you have a rooftop unit with no outside air at all, then the way you're going to have to make up for cleaning the air, basically you eliminate being able to dilute it with additional ventilation air, is that you're going to have to bring in portable equipment. So you have to bring in a Hepa filter or portable UVC lights, which can kind of help you gain those air changes per hour back through purifying the air in your space.
Great, thank you. Now there are some questions here that have been answered during the presentation, so I'm going to skip over those because this presentation will be available to everyone afterwards. The next question, I'm going to see if I can ask this correctly. It says, is running the system more often, like 24/7 recommended? And how can we do that most efficiently in terms of energy use?
Yeah, I can jump in and ask that one. If no one is there, then I don't know if you need to be running the system, to be frank. If you have people there 24/7, that's a different story. If you want to flush the building before people come in, like turn things on an hour before and kind of, most buildings do have a morning warm up or cool down cycle already, or you just program it to come on an hour early, you can do that. But I would agree, unless you have people running 24/7 or people in there 24/7 running the system 24/7 could become pretty costly over time. And I'd recommend trying to run it mainly when people are there, making sure you have good filtration, making sure you're maximizing ventilation, doing all the things that we talked about here.
Yeah, and I would add to what Jim said, that idea when thinking particularly about, was there an occupant in that space who may have had COVID and been emitting particles with COVID on them into that airspace? You don't need to run it necessarily 24/7 when it's unoccupied, but running for some time to allow air exchange after the occupants leave for the day or before they come back in the next morning. That kind of flushing the system idea Jim mentioned is great. In situations where you have a known COVID case who occupied that space. So let's say you're a workplace and you find out one of your employees has COVID, and you realize they were there at work the day before when they probably were, you know, infectious and contagious then. You might think in that situation about running your system through the space that that person occupied for, you know, 12 or 24 hours to really push that air exchange through. But if it's just on a general preventative measure, I think as Jim said, you know, think about flushing before or after, but there's not necessarily a need to continuously cycle new clean air into unoccupied spaces.
Okay, now this next question is residential, but I imagine the scenario could apply to certain commercial spaces. If you have two residential units sharing a single heating unit that can't take a different filter, can you put filters on the heat registers in the floor?
Well, the problem with that is the filters are going to slow down the amount of air coming out of the floor registers. So sure, you can do that, but it's likely going to impact the performance of your system. And let me give you a good example that I can speak from personal experience. And this is a long time ago, before I knew HEPA filters and all that stuff. It just sounded like good stuff. I put a HEPA filter in my air conditioner in my condo, and after a while, I noticed my AC stopped working, and I noticed that the coil froze up. Well, the coil froze up because the HEPA filter slowed down the airflow, which limited the performance across the DX coil. And with that slower velocity, ice started building up on the coil. And that's why I strongly encourage and discuss in this presentation that you need to work within the design capabilities of your HVAC system. If you try to do things to it that wasn't designed to do, it will impact the performance and could potentially hurt the system and also hurt the comfort of the space.
Next question, thank you. Next question is, how can I find the ESP for various MERV filters?
Yeah, I assume you mean the external static pressure of that. That would be, you know, usually that kind of stuff is buried in the fine print of the filter itself, but you should be able to look that up if you find the filter you want, and that should be within the manufacturer's information. You just gotta look for it. It's usually not on the front cover. You gotta look a little deeper for it.
Okay, Jim, you're very popular. What if your only cooling is a swamp cooler, which you can't easily filter, especially when it's super hot out? Any recommendations?
Well, swamp coolers bring in a lot. I mean, swamp coolers are 100% outside air. So you are really diluting the space significantly when you bring in the swamp cooler. And in some ways, that's even better than opening a window, because you are forcing lots of outside air into your space and through dilution. Because there's basically, you know, two methods we're talking about here to improve the quality of your air. There's, you know, diluting it with more air, and then there's filtration. You know, try and maximize both. But with a swamp cooler, you're really bringing in a lot of outside air. And I'll let Kristen add to this, but I'm not sure if you really need to add any more filtration on top of that. Now, when you don't use a swamp cooler, it's winter time, that's a different case, and you might need to bring in special filtration during the winter. But I'll let Kristen or anybody else jump in if they want to add to that.
Yeah, I don't have too much to add, except for, you know, essentially thinking about like swamp coolers or any type of modification you make to try to improve airflow or cooling, you know, fans, things like that. I think it's important to just keep in mind sort of how a proper HVAC system would be set up, which is to say, you know, thinking about that airflow movement being laminar. So rather than kind of creating a constant recirculation, you're thinking about the airflow kind of moving from a source of the air to the exhaust of the air, things like that. And so if you're doing something like putting a swamp cooler or other fans in place to try to improve the general conditions of the room, think about doing it in a way that would keep those proper style HVAC techniques in place.
Great. I have a question for you myself, actually, and this would be for both of you, or either one of you that feel most comfortable answering. But currently many buildings are only half occupied, and so if they're bringing in professionals to assess this building, and they're also planning maybe in 2 months to have 3/4 or full occupancy, how does one plan for that? In this whole getting the right expertise, planning ahead, and making sure that the outside air or other measures are effective.
Yeah, I can start with that. Yeah, controls are really what's going to help you. And part of the challenge here is that, especially a lot of our smaller buildings are literally, the rooftop units are controlled with a programmable thermostat. And that programmable thermostat doesn't allow you to sit there and be able to modify the outside air easily based off the occupancy. So you're basically either running the system or you're not. It's kind of like in your house. I'm either running the house, whether there's 5 people in it or 1 person. I'm running it the same no matter what. But there are good aftermarket controls, and even for demand control ventilation that you can actually install on rooftop units if that's what you have serving your space, that will allow you to more efficiently control things and basically match what that HVAC system is doing based off the occupancy. But it will take an investment to do that, because unless your building has a building automation system with good controls already to where you can actually tweak these things within your current control sequences, if you just have a standard building with rooftop units and programmable thermostats, that's going to be more challenging to do that.
Thank you, Jim. And it looks like we have time for, I'm going to try to squeak in a couple more questions. These are all really great.
Probably last one, Denise.
Okay, last one. I'm dealing with an old building which recirculates the air, basically no air return. What is the best way to ventilate the space?
Yeah, there's 2 options. Of course, you can replace the system. That's the most expensive option. Redesign it to bring in the adequate amount of outside air and so forth. But I doubt you have money burning a hole in your pocket to do that. And so next best option will be to use portable equipment, as we mentioned, portable filters, portable disinfection. But then even taking a step before that, I'd recommend getting an engineer in there, taking a look at what you have, taking a look at what we can, let's make sure what you have is actually working correctly. That's what I talked about with recommissioning. Let's get that baseline back to where it should be, how the building was designed to operate. And then from there, we kind of build the recommendations off of that, whether it's doing some indoor air quality testing, bringing in some portable equipment, as I mentioned. But there are options, and it doesn't have to be replacing the system right now if you're not ready to.
Thanks, Jim. Thanks, Kristen. This was I think, a fantastic presentation, and we've got probably at least another hour's worth of questions here that came in. We will take a stab at pulling answers to these questions together. Maybe Jim and Kristen, if we could get your support as well. And based on the interest in this presentation, maybe we host another just another Q&A session. We'll talk about that, and we'll get back with all the registered attendees. There are questions about the webinar is being recorded. We will post it. We'll share it with everyone, so you'll have access to it. And just again, want to say thank you to Kristen, Jim, for your time, for your expertise, and thanks for all of the attendees today for taking time out of your day for this important topic. Take care.
Thank you.